This video is about geometric vectors, an introduction, and two applications, addition and scalar multiplication. We've seen in our previous introductory work that there's a difference between scalar and vector quantities. So quantities that have both direction as well as magnitude can be represented by arrows if we draw them, and basically these are called vector quantities. On paper or on a screen, they are geometrically drawn as directed line segments. Scalars cannot be drawn with arrows. Scalars are magnitude only. In the diagram to the right of the screen, we see an example of 5 directed line segments that both have the same direction in the magnitude. They're all in different positions on the plane, but they have the same direction and magnitude. So they could be seen as equivalent in some models. In our previous work, we looked at storage vectors. Basically, they're a column array, or there's a word you'll learn later called matrix. They're basically a column matrix or a column array of numbers, or they can be written as a row, and that means the same thing. So it's an equivalent idea to a geometric vector. So a geometric vector is when we draw it, we draw the arrows, and the other way that we know at the moment is called the storage vector, which is written as a matrix or an array. So they have equivalent meanings. They have different purposes usually, however. If we look at the example here, AB, if the vector is called AB, which means it starts at A and goes to B, if it equals the column vector 3, 2, or the storage vector 3, 2, we can write that or draw that as a geometric vector. So notice we've got a Cartesian-like axis system here, which you are familiar with. The first number means in the x direction. The second number in this model means the y direction. So it goes from start to end, and then it undergoes 3, 2. So 3 across and 2 down. In red, the red vector you see there is the result. As we saw with our early work on storage vectors, vectors are often denoted by single boldface Roman font type letter, like that one there, like that V. It's got to be in bold. The vector from A to B can also be denoted just like a line segment. It's got a direction, however, so not AB like this. It has to have the arrow there because it has a direction. The other way is using a tilde, which is a little squiggly line that goes underneath, a tilde. Occasionally you might see spell tilde as it sounds tilde, but that's the proper spelling tilde. So that's what that little squiggle is. Again, that denotes that it's a vector quantity and not a scalar. If they are scalars, they do not have boldface or they do not have tildes. If they're vectors, they need to have one of those two, or more rarely they will have the directed line segment notation. It's important to distinguish between vectors and scalars. The first operation that we're going to look at with regards to geometric vectors is the addition of vectors. We've already had a look at this in terms of storage vectors. Examples of where this is used are plentiful, and one example might be where we have basically the intended path of a boat. However, we also have the influence of the current if it's travelling down a river, and then we have the actual path of the boat. Navigation is one example where this is used quite extensively, where you could have maritime or aviation type navigation. So addition of vectors, we've seen how it works with storage vectors. How does it work with geometric vectors? If we have u and v here, you can tell u and v are denoted as vectors with their bold face. U plus v, we put the two vectors u and v head to tail, Now it doesn't help in this diagram that the arrows are halfway along. I often write the vectors with the arrowhead on the end. That's more useful. So if we put them head to tail, so there's the head of vector u to the tail of vector v, and there's the head of vector v. And the difference between the start and the end, if we join them up with another vector, that is the resultant. That vector is called u plus v. It's the result of adding u and v. When you add two vectors together, you always get another vector, just as with the storage vectors. Vector addition is commutative. So from your early work you might know that commutativity is where of addition anyway, is where you add things together, and if you change the order of the addition, the result is still the same. So u plus v equals v plus u. We can show that in a number of ways. We can show that geometrically with this diagram here. U plus v head to tail, we get the blue vector. V plus u head to tail, we still get the blue vector. Okay, because we're joining the very beginning to the very end is how we come up with our resultant vector. So the v or u first, it doesn't matter, the result is the same, they're equal. To further demonstrate this, in our previous work, if we were looking at storage vectors and adding them together, if we define u and v as such, u plus v, we add the corresponding elements. So 4 plus negative 1 is 3, 3 plus 1 is 4. So how does that look? Again, with the vectors geometrically drawn, if we have a starting point here, u to v head to tail, I would prefer if we put our tails, our heads on the end, okay, so they go up against the tail of the other vector. If we try u plus v, we have a vector that's moved across a certain amount, and in this case the amount it's moved across is 4. It's then gone up 1. It goes across negative 1 because it's going back in this negative direction, and then it goes up a further 3, and the final vector is 3 across and 4 up from where it began. And you can see that that matches our answer over here. Okay, so the result was 3 across and 4 up from where we began. Notice how the vector u there was 4 across and 1 up, hence the 4 and the 1, and the other vector was 1 back to the left, which is the negative 1 in the x direction, and up 3. So we get 3, 4 in total. As with storage vectors, we have this thing called scalar multiplication. A scalar is just a real number, and it says non-zero here. 0 is a special case which we'll go through in a second, but if we deal with 0 separately, we'll look at non-zero real numbers. But as you know, real numbers are everything basically except for complex numbers, which we keep external to this study of vectors. If we have u plus u, that's the same as 2u. It's 2 lots of u. That 2 is a scalar and the u is a vector. If we drew that geometrically over here, let's say u is this vector, 2u is twice the length. However, the direction is the same. Same direction, but the length is multiplied by a factor of 2. When we multiply by negative 2, or any negative value, the negative 2 reverses the direction of the geometric vector. So again, if we start with that same u, it's like the answer above, except for we've put the arrowhead on the other end. It's got the opposite direction. However, the magnitude is, well, the length of the arrow is the same, but it's just that the magnitude is in the opposite direction. The magnitude is the same, sorry, but it's heading in the opposite direction, same magnitude. As I said, 0 vectors treated separately. It's when we have it's equivalent to a scalar multiplication of 0. The 0 vector does exist. It's important for a number of things. We exploit its property a lot, and in vector proofs we'll be looking at the zero vector more. It basically has a length of 0 and no defined direction. It's impossible to define the direction of the zero vector, however it does exist.